Okay, we're going to spend 3 days going over 4.5 so that you have a really good grasp of what we're talking about. So the first day we're going to talk about linear regression. Scientists often use a linear regression to model data in order to make predictions. Remember the crystal ball. A linear regression models the relationship between two variables in a dataset by producing a line of best fit. A line of best fit is the line that best approximates the linear relationship between two variables in a dataset. The equation that describes the line of best fit is called the linear regression equation, and that's what we're going to learn about today. So linear regression consists of finding the best fitting straight line through the points. The best fitting line is called a regression line. So I've just drawn a few of these here. Remember that the actual data points are the dots. So this is an actual data point, and this line represents predicted, okay, or estimated data points. Okay, very few ever have a point on the line, but it happens every once in a while. You can see that each one of these has a point or two that is on the line, but that is rare. So we create a line of best fit that approximates the movement of the data. And this allows us to analyze the data and even make predictions. Okay, so here is the actual formula that we use. Kind of scary. And this is on page 167. This is what happens with it, how they get those things, what each of the parts means. I'm not going to go through this because you're going to learn to do this on the calculator. Thank goodness. And you don't need to memorize this. Okay, so the scatter plot here shows the median age of women, American women, at their first marriage for selected years from 1960 through 2010. To find the line of best fit, you can use a computer, spreadsheet, or graphing calculator that has a linear regression feature. So we are going to turn on our graphing calculators right now, and we'll be ready to figure this out. Okay? So we take each piece of data and we put the XY, so this is 1960 is year 0, and the answer is 20.3. So these are the actual ages that we were given. And you might be given them in a table. Chances are you're not going to have to take them from the graph. So we enter all of these into our database. So L1 is all the X's, and L2 is all of the corresponding Y's. You have to make sure that each X and Y is from a corresponding point, okay? So make sure you remember that the year, if you're using years, the first year is 0, and everything after that would be the distance from 0, okay? So 1960 is year 0, 1965 would be year 5, 10, so forth, okay? So make sure that you understand that because you're going to be asked to do that in the future. So what does the ordered pair 25, 23.5 mean? If 1960 is year 0, then we just add 25, and it would be 1985 is year 25. And it means that the median age of women in their first marriage that got married in 1985 was 23.3. Okay? So that's what you want to do. So now you're going to turn on your graphing calculator, and I'm going to show you how to do this entry part. Okay? So first thing you have to do with your calculator is go to diagnostics and turn them on. So that means you go hit the second button and the catalog button, which is your 0. So you hit second, and then you hit 0, and then you hit D. Okay, and that is above this line. And then, because the catalog takes you automatically to that, so you go to D, and then it takes you to the D in the alphabet, and you scroll down, just enter down until you get to diagnostics, and make sure they're turned on, and then hit enter 2 times. Okay, so follow those instructions, and when everybody's got their diagnostics on, then we're ready to enter our data. Remember, these are your X's, and these are your Y's. Now, it's totally okay if you're using a table to enter all your X's and then go over and enter all your y's. That's the fastest way to do it. But I would suggest that afterwards you go back and make sure that they've lined up. You don't have an extra number down here or over here, and just check a few to make sure that they are exactly what the data showed you. Okay, so now we're going to go ahead and enter the data. We're going to hit the stat key. Okay, we're going to hit enter, and you're going to hit number 1, which is edit, and it's going to take you right to here. And so you just enter all the x values. When you're done with the last x value, you're going to arrow over. So you'll have that button that has the little arrows like this. You're going to arrow over, and it'll take you to the L2s, and then you can enter all the y's. Okay, now when you're done with that, you're ready to go to the next step. That's calculating the equation. So you're going to go back and hit stat again. You're going to arrow over to calculate. Then once you click on calculate, so press on calculate, and then you're going to scroll down to number 4, and it looks like this. Make sure you go to number 4. Then it's going to ask you to check that it's L1 and L2. Make sure that this was L1 and L2. You should have checked that at the beginning. Then you're going to scroll down there to calculate, and you're going to hit enter 2 times. Okay? Now, what's going to happen is this is going to pop up on your screen. So it's showing you how the equation should be put together. So you can see we have the A right there. So this is our slope. And there's the B. This is our y-intercept. Whoops, intercept. And then we're not going to ever worry about R2 and IM1 or IM2, but we are going to use this. But we're going to get to that in a minute. So now we can take this information and we create our linear regression equation. So here it is. Okay? So here's the equation, but man, those are big, big numbers. So one of the first things you're going to find out with linear regression is you're going to put it in significant digits. So usually that's tenths. If we're talking about money, it would be to hundredths, but some people even put this, okay? Because we're talking about age and we're approximating, so we can approximate, okay? But we don't simplify the slope. All right, so now we've got this equation. What does it all mean? What does this mean that I told you about? Okay, this we're not going to use, but what does that R mean? So let's go to that next. Graphing calculators use a method called linear regression to find a precise line of fit. This line best models a set of data. A calculator often gets a value R called the correlation coefficient. Okay, we're looking at this one. Do not look at the R squared. These are the names for it. R value or the correlation coefficient. This value tells whether the correlation is positive or negative and how closely the equation models the data. Values of R range from -1 to 1. When R is close to -1 or 1, there's a strong correlation. So look at this. Strong negative correlation. Strong positive correlation. But if it's right here or right here, that is no correlation. Okay, around here. This is a weak correlation. And this is a weak positive correlation. So you have to understand that these are both great. Okay, these are both strong correlations. So that's what your R value tells you. It tells you 1 is a positive or negative correlation. And then 2, how well does the equation, the regression equation, fit the line or express the line, express the data, fit the data, okay? So how well does the regression equation fit the data? So we'll go into that in a little bit more detail here. So I did want to point out that you can also tell that it's going to have a positive slope when your slope is positive. So the slope, the sign of the slope should always match the sign of your R value. And they will both tell you the positive or negative correlation. Okay? But these are the two things that your R value tells you, that your correlation coefficient tells you. So remember those. Okay, so now I've got to erase all that so I can show it to you. Okay, so show all this. All right, so there's the regression equation, and we already had the equation, but there is the line of best fit, okay? Okay, since we're going to be doing a couple more problems, you're going to want to reset your calculator. So you're going to hit the second, and then you're going to hit memory, which is the plus sign. And then when you hit that plus sign, it's going to take you to a list. You're going to scroll down to number 4, and then hit clear all lists, and clear all lists again, and it'll tell you done, okay? All right, let's look at a couple more problems. Okay, we are not going to calculate the next 2 slides that we go over. I want to show you some hints and reminders and what the things mean. So just put your calculators down for a minute and listen. So as the Earth's population continues to grow, the solid waste generated by the population grows with it. Governments must plan for disposal and recycling of ever-growing amounts of solid waste. Planners can use data from the past to predict future waste generation and plan for enough facilities for the disposing of and recycling the waste. So the first thing I want to look at is, this is my x-axis. Okay, but when I'm calculating, I need to remember that if it's a year, I start with year 0. Okay, and I make sure that this is the next year and the next year so that my numbers match. And this would be our y's. So when we're entering things into the calculator, we don't enter the year 1990, we enter 0. Okay, so once we've plugged that in and hit our magic buttons, it's going to give us this calculation. So I want to go over what exactly this calculation, this equation means in terms of this problem, because I will be asking you for that on the test, so you need to understand that. Okay, so first thing we want to say is the tons of solid waste generated in Florida is increasing by 1,042 tons per year since 1990, when it was about 18,754.8. So we're going to go through this step by step and point out what each thing represents. So the first one is the tons of solid waste generated in Florida. That is our Y. Okay? It tells us right there. And we added the Florida because it told us that up here in the introduction, in the title of the table. Okay, so the tons of solid waste. So Y equals, the next number that we come up with is increasing. Well, we know that because this is positive, right? And we also have a positive R, so that helps as well. Increasing by 1,042 tons. So that is our slope. It's increasing by 1,042 tons, okay? And the next thing we want to mention is per year, and that is our X value. We can see right here, there's X. So per year, it's going up. And then it says since 1990, year 0, when it was about 18,754 tons. So right here, we're looking at our y-intercept, okay? Notice that this is not the same as our y-intercept here, okay? It's not always going to be. We talked about how the linear regression equation does not always match exactly the y-intercept. Now, when you're giving this explanation, you're going to use your predicted values. You are not going to use the values from the data, okay? So make sure that this is the same as that. Now, I'm going to look at my R value, and my R value tells me that this is a positive correlation. Come on, pen. There we go. Positive correlation. And since it's really close to 1, it's a good fit for the data. Okay, you could even say it's a great fit for the data. So this equation is a great fit. It expresses the data very well. So that means we could make good predictions with it. Okay? All right, let's look at the next one. The winning time in minutes in the women's 400-meter freestyle swimming event in the Olympics from 1936 to 1996 are given by the following ordered pairs. So you have to look at this as X, Y, X, Y. The problem is our X's are not the ones we should use, right? So we're going to hit the button, and we're going to notice that 0, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56, 60. Oh, it's going by fours. The Olympics used to take place every 4 years. The Summer Olympics still does, but all the Olympics used to be held every 4 years. Okay? So here's the equation, and now we're going to interpret it. Okay? So the winning times in the women's 400-meter freestyle event. So the first thing we're going to look at is, what was the title of my whole thing? The winning times in the women's 400-meter freestyle swimming event in the Olympics. Okay, I got this from this sentence. Okay, so that is my Y. Then I'm going to look. I have a negative there, so it's been dropping. See that negative right there? By about 2.7 seconds. Okay, we know that that's seconds because it says the winning times in minutes, and this is 5 minutes and 44 seconds. But so that means it's dropping by seconds, and that is our X value. So you want to make sure you get that. So that's our X value. And then per year since 1936, when it was about 5.4 seconds, and there is our Y value. Now this Y value is pretty close to the Y value we were given for year 0. And what does this tell us? It tells us that we have a negative correlation. As years go up, the time is going down. So it's a negative correlation. And it's a very good fit for the data. So the equation, this is telling you what the equation is. It's a very good fit for the data. Okay, there you go. So it's talking about the equation is a good fit for the data. Alrighty, so let's turn our calculators on and try one more problem and see how you do with that one. Okay, as the number of farms has decreased in the United States, the average size of the remaining farms has grown larger. So we have the number of farms is going down, but the acre per farm is going up. So calculate a regression equation to show the increase. This is the increase on the farms that survived, okay? So this is our Y. Now we've got to be very careful here because we've got 1910, 20, 30, 40, 50. Then we go to 59, 69, 78, 87, 97. So when you're making your X's, you have to calculate what that would be. So like if I said 1910 to 1997, that's an 87 difference. So we're going to go ahead and plug those in. So I want everybody to take the time to plug this into your X's and this into your Y if you have a graphing calculator. Otherwise, come by during lunch one day and I can show you how to use the calculators. Okay? Alrighty. So now we're going to come up with the equation. So you're going to do all the steps that were before. I've given you a piece of paper to help you with that. So go ahead and see if you can come up with the equation. And push pause here if you're doing that. Otherwise, we're just going to go through it. Okay? All right, so here's the equation. It's telling us that the average acreage per farm is increasing by 4.72 acres per year since 1910, the first year of the study, when the average size of a farm was 85.11. Now, look how different this y-intercept is from this y-intercept. That's quite a big difference. So, before you turn off your calculator, I want you to make sure that you clear all lists. That should be on your paper too, and then you can shut it off. And thank you for following directions, and have a good day.